Welcome to this first class of this exciting 4-session course on working with LEDs using Arduino. In this class, we'll be using the onboard LEDs of the Circuit Playground microcontroller to make our first LED animations. You'll also learn about different LED products, a bit about current power, and all about how LEDs work. You'll also get your first taste of working with FastLED, a powerful library that will help us program our LEDs. I'm Mirabelle Jones, and I'll be co-teaching this class with Cathy Laughlin, who you can meet during our optional office hours. Let's get started. You'll get the most out of this course if you go to mirabellejones.com/hackaday_LEDs, and there you can access the course files. That'll include this slideshow and also a link to the GitHub, which has all of the source code you'll need to follow along with this class. Feel free to head over there now. We're going to be using the Circuit Playground microcontroller in this class. But what is a microcontroller? A microcontroller is an electronic device which is capable of doing one or more tasks. It is made for embedded systems and is often used in automatic control systems. It consists of memory, I/O ports, and a processor. A microcontroller unit usually comes with a breakout board which might extend its capabilities. Here are some popular microcontroller units. There's the Teensy, the ESP32, a Pro Micro, and on the left we have the Arduino Uno, which is often just called an Arduino. We're going to be using the Circuit Playground Express, which is a newer microcontroller loaded up with goodies for us to play with. The Circuit Playground Express has 10 Neopixels already on board. It has a temperature sensor, it has a light sensor, it has a speaker, a microphone, a slide switch, 2 buttons, and it also has capacitive touchpads, which we'll be using today. Let's get set up. First, you'll want to install the Arduino IDE. To do so, you can go to arduino.cc, and under Software, you'll see a download link. You'll want to download the correct version, whether you're on Mac or PC. Once you're at the Arduino homepage, you'll want to go to Software, and then go down to Downloads. You'll also see that there's an Arduino web editor, but we're going to download the Arduino IDE. If you scroll down, you'll see that the latest version of Arduino is 1.8.13. To the right, you'll see different installers. Select the installer for your operating system. I'm going to select Mac. Arduino is open source software. You can contribute to its development here, or you can just click Just Download. You'll be prompted to save the file. Click OK. Once the file is finished downloading, you want to open it up. It should automatically expand. If you're on Windows, you're going to also want to install the Circuit Playground driver. You can find it at the following URL. Just follow through with what it says to do, and you'll be all right. This requires a special driver. You're going to want to go to the Adafruit website to find this. You can also just Google Windows driver Adafruit Circuit Playground Express, and it should be the first option that comes up. Once you're on the page that says Windows driver installation, you'll see a big green button that says Download Latest Adafruit Windows Driver Installer. Click this in order to download and run the installer. Then follow the instructions. Now we're going to want to install the library. In Arduino, we're going to go to Tools, Manage Libraries. In Library Manager, type Circuit Playground Express into the search bar. Then click Install on Adafruit Circuit Playground Express. Now we want to install the library. You're going to want to go up to Tools, Manage Libraries, and then you'll have the Library Manager pop up. We can type in Circuit Playground, and the Adafruit Circuit Playground library will pop up. Unlike the boards, there's just one library, so you only need to worry about installing the Adafruit Circuit Playground library for both the Adafruit Circuit Playground board and also the Adafruit Circuit Playground Express. To install it, select the version that's most recent, then click Install. Now we're going to install the board. In Arduino, you're going to want to go back to Tools, and then under Boards Manager, which is under Board, you're going to type in Circuit Playground Express into the search bar. You can also type in SAMD boards if you don't see it. Be careful because there's actually two versions of the Circuit Playground. There's a Circuit Playground and a Circuit Playground Express. And we want to install the Circuit Playground Express, which is under SAMD boards. Once that comes up, click Install to install the latest version. To make sure that you have the right board installed, you want to go to Tools, Board, Boards Manager. Here you should type in SAMD boards. You'll see that under SAMD boards, the last option is Adafruit Circuit Playground Express. Beware that if you just type in Circuit Playground, you'll get two different things pop up. One of these is SAMD boards for the Adafruit Circuit Playground Express. The other one is for Adafruit Circuit Playground. We're going to want to select Express because that's the controller that we have. If you select the most recent version and then click Install, it will begin the install process. Now you want to plug in your Circuit Playground in Arduino. Go to Tools, Board, and then select the Circuit Playground Express from the list. If you don't see this as an option, you have to install the SAMD boards. Go back a few slides and then try again. To select the right board, we go down to Tools, Board, and then we want to make sure that under Arduino SAMD boards, we have Adafruit Circuit Playground Express selected. Make sure that if you have an Adafruit Circuit Playground, that you don't select that for the Express. In order to make sure that we have the right port selected, we want to go to Tools, Port, and then depending on whether or not you have Windows or Mac, it might look a little different. For me, I have /dev/cu.usb modem and then a number. I also have in parentheses Adafruit Circuit Playground Express. If you have an older Mac, you might not see Adafruit Circuit Express pop up, but as long as you have something that says dev or USB modem, it's probably the right port. To create a new sketch, we go to File, New. Every sketch will be labeled with sketch underscore and then the date by default, but you can change this later. You should see a blank Arduino sketch. The two main functions in any sketch are filled in for you. Setup, which runs when the Arduino first boots, and loop, which runs constantly in a loop after setup finishes, and for as long as the Arduino is powered on. If you're a beginner with Arduino, see here for more on functions and what they do. An LED is a light-emitting diode. When current passes through the LED, it causes the LED to light up. In addition to finding some of the code that we'll be using in this course in the Adafruit library, you can also find it on GitHub at github.com/Cathy Laughlin/Hackaday_LED_class. Once you're there, if you click on the green button that says Code, you'll be able to download all of it as a zip file. Before plugging in, place your Circuit Playground on top of the bag it came with or another anti-static, non-metallic surface. Never let the back of the Circuit Playground touch metal when it's plugged in, otherwise you could short it out. Next, plug in your Circuit Playground via micro USB cable. You should see it light up with its initializing pattern. To get to our example sketches, we want to go to File, Examples, and then down to Adafruit Circuit Playground. Here you'll see a whole bunch of sketches that you can use. You can really dig into these to learn how to use the microphone, the light sensor, and more. But for starters, let's just blink this LED. To get to the blink sketch, we want to go to Hello Circuit Playground. Underneath Hello Circuit Playground, there are some introductory sketches that should get you started using some of the onboard sensors of the Circuit Playground. Let's start with Blink. In this sketch, we see that we're including the Adafruit Circuit Playground library. This is the first line of our sketch. Then we have a setup function and a loop function. These are the two main functions in Arduino. In our setup, we're initializing the Circuit Playground, circuitplayground.begin. We'll need to do this every time we want to use any function that's in the Circuit Playground library. Then in our loop, we're saying circuitplayground.redLED high. Then we have a delay of 500 milliseconds, or half of a second. Then we're saying circuitplayground.redLED low, and then have another delay for half a second. What this sketch is doing is it's targeting the red LED, which is D13 on the Circuit Playground Express. This is an indicator LED that's a single color LED, just like the one that I showed in the video. This LED will light up when current passes through, again, just like I showed in the video. So what we're doing is we're saying high, which is sending the maximum voltage that we can to this LED, 255. Then we're setting it to low, meaning that we're setting it to 0, the lowest amount that we can send it. And we have a delay in between. So when we upload this, we should see the LED blink. Let's give it a try. To upload a sketch, you want to go to the arrow at the top. If you hover over this, it'll say upload. You also want to make sure that you have the correct board and port selected. Once you know that this is the case, click the arrow to upload your sketch. You'll see the LEDs on the Circuit Playground go from red, then to green. When they've gone to green, you know that it's been uploaded correctly. When you upload a new sketch, the LEDs on the Circuit Playground Express will first go from red, then to green, and then your sketch will run. Now we can see the red indicator LED D13 blinking. If you encounter any problems uploading your sketch, you can press the reset button twice and reset your controller. For your first challenge, try going back to the sketch and trying to get the LED to blink at a different rate. As a hint, try using a different delay value. What is a Neopixel? Each RGB LED, or Neopixel, is actually made up of 3 smaller LEDs, one red, one green, and one blue. The combination of these 3 color channels creates the visible color of the LED. When all 3 colors are turned on, you'll see white, and when none of them are, that's black. So black is always equivalent to off. Other colors are created by mixing the 3 color values. You can try this out for yourself by using the Hello Neopixel sketch. Try changing the last 3 numbers in the parentheses to mix the red, green, and blue color values. Let's give this a try. We see our LEDs light up with various rainbow colors, and then they go black. This happens at a half-second cycle. It's nice having source code to use, but we learn best by trying things ourselves. Let's try changing the values in circuitplayground.setPixelColor to make our own colors. Can you try changing the pixel number and also the RGB values? In the first challenge, just try making your own colors. Have fun and experiment. For the second challenge, try turning all of them to purple. For the third challenge, try turning them all to white, and then all off, and then all white again. For advanced users, try using a for loop to set the color of all the LEDs at the same time. Or try making your own animations. This principle of finding an example or demo sketch and then experimenting with the functions and also the variable values in order to see what they do will serve you well when learning Arduino. Programmable RGB LEDs use an onboard driver chip to turn the electrical signals on your data wire into programmable colors by setting the red, green, and blue channels accordingly. The library we'll be using, FastLED, can handle most programmable LED drivers. The most commonly used are WS2811, 2812, and 2813. Adafruit's Neopixel line are some of our favorites due to the wide variety of products they offer, but you can also find more affordable products online. Individual LEDs. You can get surface mount, through-hole, and even sewable LEDs online. These can be great for embedding subtle lights into projects or wearables without ending up with an overt light strip look. LED strip, the LED workhorse. Strip comes in densities from 30 LEDs per meter to 144. Higher density strips require more power. Note that LED strip is easily damaged if you don't take care when installing it. It's best to not bend or crease LED strip, so if you take it around a corner, it's best to cut the strip and solder some jumper wires between the two strips. LED modules. These are individual RGB LEDs, each sealed into its own waterproof module with a diffuser. Short wires, typically 4 inches, separate each module from the next. Great for a light bright look or for embedding individual pixels into the surface of complex outdoor artworks. LED matrices. These come in square or rectangular formats. Larger matrices require more power. The LEDs in your matrix can either be wired across like a typewriter or back and forth like a snake. FastLED can address both as long as you tell it which type you have. If your matrix doesn't say, then don't worry. Experimenting is an easy way to find out. LED rings. These come in sizes from about 12 LEDs up to 60. The larger rings require 2 power injections. We'll talk about those later. The smallest can be powered off an Arduino as is. These look cool as they are, but they're also fun to embed inside round objects. They can make cool eyes if you install them in pairs and are careful with the programming. Side-emitting LED strip. These are powerful when you want to use LED strips, but you need to attach the lights to the inside of a solid shape, such as a tube or half dome, or need them to shine out rather than up. Unlike regular flat strips, these strips can bend to an extent without damage. LED neon. These LEDs are embedded inside a thick neon-look diffuser. They're quite flexible, making them perfect for lining complex surfaces, using as recessed lighting in a room, or making neon art. Now it's time to make our own animations using the FastLED library. FastLED is a powerful library that allows us to make many patterns and animations pretty easily. Before we can use FastLED, we need to install the library. To do so, we'll go to Manage Libraries and add FastLED. We can find it using the search bar. Just click the latest version and click Install. Once it's installed, you'll find all the example sketches under File, Examples, FastLED. If you've used FastLED before, you can feel free to try the other example sketches. We can use any FastLED sketch with the onboard LEDs of the circuit playground by changing the data pin to 8. All of the onboard circuit playground LEDs are wired to pin 8. We'll also need to change the number of LEDs to 10, and if there's a clock line mentioned, we'll need to comment that out. To install the FastLED library, go to Manage Libraries. Then type FastLED. There might be several options that pop up, but you want to choose the one that just says FastLED. Select the most current version and click Install. Once it's installed, open up FastLED's Blink sketch. This can be found under Examples, FastLED, and Blink. You'll notice that this sketch looks very different from our other Blink sketch. This is because FastLED programs lighting a little differently. First, what we'll want to do is comment out clock pin. We can do this with 2 forward slashes. Then we want to change the define for data pin to 8. 8 is the pin that all of our LEDs on board the circuit playground are connected to. Then we want to change the number of LEDs to 10. There are 10 onboard LEDs. Double check your values, then hit upload. Only one LED is blinking. We changed num LEDs to 10, so why don't all of them work? Here's why. LEDs within FastLED are treated as elements in an array. You can see the array declaration on or around line 14. If you don't have line numbers turned on, you can go to Preferences and then check Display Line Numbers. So on line 13 we see CRGB LEDs num LEDs as an array. This tells FastLED we would like to reserve space for an array of 10 CRGB objects, aka RGB pixels. Note that this line always goes at the top outside of the setup and loop functions. Below, you'll see the following line in setup: FastLED, add LEDs, Neopixel, data pin, and then in parentheses, LEDs, num LEDs. This tells FastLED that you have Neopixels on data pin. They're to be stored in the LEDs array, and there are num LEDs of them. You always need a FastLED.addLEDs call in setup when working with FastLED. There are many options for this line since there are many kinds of LEDs in the world. Check out the other entries for some possibilities. Anyway, scroll down to the loop function, and we'll see why our LEDs aren't lighting up. In loop, our code says the following: LEDs 0 equals CRGB red. Then there's a call to FastLED show, which is a function of FastLED. Then we have a delay of ½ second. What this says is, light LEDs number 0 to red, then call FastLED show, then wait ½ second before continuing. Then the code does the exact thing to set the LED at 0 back to black, completing our blink cycle. These 3 lines represent the fundamentals of any FastLED sketch: code that changes the values in the LEDs array, a FastLED.show call, and some timing code. At its ordinary speed, the Arduino operates much too fast for humans to perceive, so we need a way to change our lights more slowly. Note that delay is not the way you should do this in non-demo code. We'll explain a better way in the next class. The only confusing thing here is FastLED.show. Use this call whenever you want the strip to update. It'll cause FastLED to write the contents of the LED array out to the actual lights. Often you'll use just one FastLED show call at the end of your animation loop, after you've made all the color changes you want to make. This is important because FastLED.show can be an expensive call in terms of time. If you can call it just once per timing cycle, you'll improve the efficiency of your code. In the case of this demo, however, we have 2 show calls inside the loop, one for the red color change and one for the black. And this also happens to answer our question from earlier. Only one LED is blinking because we're only changing LEDs 0, which is the first LED in our array. Note that arrays always count from 0 and stop at 1 minus num LEDs, in this case 0 through 9. It might seem intuitive to copy and paste in order to get all of the LEDs to show. But this takes a long time. Maybe there's a better way to do this. When you have this many pixels, it's not really practical to copy and paste. Thus, we're going to use a control structure called a for loop to do the work for us. Change your code to look like so. First, we're going to write for, opening parentheses, int, which stands for integer, a number, I, which is a variable, and we're going to start at 0. While I is less than num LEDs, which we already set earlier to 10, then we want to increase it, I++. Now, what we want to do is instead of changing 0 to red, we want to change any LED that is I to red. Then we're still going to do FastLED show and then a delay. Now we want to do the same thing for turning the LEDs off. You can type this out again, or you can copy and paste. Again, we're going to have this for loop, and then instead of changing it to red, we want to turn them off, which remember is black. Let's give this a try. Now let's try an experiment. What if in our for loop, instead of having I as less than num LEDs, we had I less than num LEDs divided by 2? Let's try this for both of our for loops. What do you think will happen? Can you guess? We'll see the first half of our LEDs light up. Let's make another change to our sketch. What if instead of dividing the number of LEDs by 2 for our up to in our array, what if we changed int I to equal the number of LEDs divided by 2? Let's try doing this in both of our for loops. Can you guess what will happen? Now we see the other half of our LEDs light up. By this point, you may have worked out how for loops work. You give them a starting point and an ending point, and instructions to execute at each step of the loop, in most cases I++, which is a shorthand way of writing the most common iterator, I equals I plus 1, aka do this for every entry in the array. Let's go back to our basic for loop. What if instead of having I++, since this means I equals I plus 1, we had I equals I plus 2? Let's try making this change for both of our for loops. Can you guess what will happen? Now we see every other pixel blink. I bet you get the picture. You'll use for loops later on to develop more complex lighting patterns. To read more about for loops, see the reference here. One important thing to remember when experimenting with for loops is that trying to write to an array element which is beyond the end of your array, as defined in num LEDs, may cause crashes, freezes, and other undesirable effects. Likewise, reading beyond the end of an array will return unexpected values, because you're actually reading them from whatever happens to be stored right after your array. These off by 1 errors are an extremely common cause of bugs, even for seasoned programmers. So always check your code to ensure that you don't access any pixels beyond the end of your num LEDs array. When you're finished, save the file. We'll call it Basic LED Playground. You can use it as an example later on. Lastly, we're going to upload a very pretty demo for you to study or stare at before the next class. Go to File, Examples, FastLED Color Palette. As above, change data pin to 8 and num LEDs to 10. Hit Upload and witness the firepower of your fully operational Circuit Playground Express. For the next class, have a look through this sketch and see if you can figure out what's going on. In the meantime, let's talk more about LEDs on and off the Circuit Playground. Our WS series LEDs have 3 wires or solder pads, 5-volt power, ground, and data. The wires are usually red, black, and green or blue, respectively. To control them, you'll need to connect the data to a digital pin on the Arduino, the power to an external 5-volt DC power supply, and the ground to both the ground on the Arduino and on the power supply. The Circuit Playground has 10 LEDs which are already installed for you, and these use pin D8 as their data pin. To use an external LED strip, matrix, or other device, we'll need to connect the data line from our strip or matrix to a data pin on the Circuit Playground. To drive more LEDs than are on board the Circuit Playground, you'll need to connect them to an external power supply like one of the ones shown here. This is because Arduinos can only power a handful of pixels from their 3.3 volts or 5-volt pins. Once you have more than 10 pixels attached to an Arduino without any external power, odds are that you will underpower your Arduino, causing light glitches or freezes. If your Arduino freezes at any point during lighting programming, power down the Arduino and your lighting power supply. Disconnect the lights from the Arduino and then power the Arduino up again. If you don't see freezing with the lights disconnected, this is an indication that you need to add external power to your LEDs before you continue. Also, when RGB LEDs are not getting enough power, they tend to color shift. If this happens, you'll see the colors on the end of your strip shift towards red, since the red LED on the chip is the one that requires the least amount of power. The others brown out first. If you start to see power drop or color shift along your strip, you should add additional power to the end of the strip. It is acceptable to power a small amount of LEDs off of the circuit playground itself. To do so, you need your LED strip and you need 3 alligator clips. You'll want to attach both of the grounds, if there's 2, there might just be 1, to the black alligator clip, and then attach power to the red alligator clip. Finally, attach your data line, which could be white, green, blue, yellow, or another color, to the green alligator clip. If you're following along with a matrix, a pixel ring, or something else, you can set it up the same way. You just want your red alligator clip to go to 5 volts. You want your black alligator clip to go to ground, or GND. And then you want your green alligator clip to go to data in, which is usually DIN. Attach the other end of the green alligator clip to A7 on your microcontroller. Attach the black alligator clip to ground. There are 2 grounds on the circuit playground, and either one is fine. Then attach the red alligator clip to V out, which stands for voltage out. Make sure again that your power and ground are not touching and that your data is not touching. Now it's time to upload our code. To test our strip, we can use any of the FastLED example sketches. To find these, we're going to want to go into Arduino, go up to File, Examples, and then down to FastLED. Let's choose Cylon. In this sketch, we see we're including the FastLED library. Then we're defining the number of LEDs. Let's change this to 10. We don't want to power too many LEDs off of the circuit playground microcontroller. If we power too many LEDs off of our microcontroller, we can hurt our equipment. So let's limit it to 10. This number should also include any LEDs that are on board the circuit playground. So if you are already powering the onboard LEDs of the circuit playground, it's a good idea not to power additional LEDs off the board. In this case, I'm only going to be powering an external strip, so it's okay. And then down here, I see that it's asking me for a data pin. I've connected my data to A7. The circuit playground has multiple input-output pins. To know which ones these are, however, it's useful to look at a pinout map. You can find the pinout map for Adafruit Circuit Playground by typing in pinout circuit playground express. The first result you get should be Pinouts Adafruit Circuit Playground Express, and it's on the Adafruit website. Here you'll find information about all of the pins on the Adafruit Circuit Playground Express. There's a big map that'll show you both the digital pins and the analog pins. The digital pins are in purple and the analog pins are in green. You can also see an overview of the I/O at the top of this map. If the map is too confusing, you can also scroll down on the same Pinouts page and you can find information about important connections on the circuit playground. For example, it'll tell you about input-output pads, and it will also tell you what each pin is. So if I go down through this list, I see that A7 is also D1, and that this pin can be digital input-output or analog input. This pin also has pulse width modulation output. It also has serial transmit, and it can be used as a capacitive touch sensor. Each pin has different capabilities, so it's good to have a look at this if you're wondering where to attach your components. It also has a list of internally used pins. These are pins that are reserved for the onboard circuitry, so things like the built-in light sensor and temperature sensor. We're not going to be covering those in this class, but I do have another class that's in sensors in case you're interested. You can sign up at HackadayU. Now that we know which pin A7 is, we can change it in our code. So let's change it to 1, which is the same as A7. We now see a define statement for a clock pin. This is because some LED strips use a clock line. This is in order to keep specific timing. We don't have this, so we can comment it out by including 2 forward slashes. This will gray out the text, and that means it'll be treated like a comment. This is useful if you want to write notes to yourself or others about what's going on in your code. The rest of the sketch looks a little familiar to us. Let's upload it and see if we can figure out what's going on. We see a rainbow pattern on just 10 of our LEDs. The rainbow pattern only affects 10 even though there's more than 10 LEDs because we set the number of LEDs to 10. Programming short strips like this can be useful when you're prototyping, but to power more LEDs, we'll need a power supply. An electrical circuit is the path through which an electrical current travels. In this diagram, we see a battery and a light bulb. These two, when connected with wires, create a simple circuit. We might add a button in the middle of the circuit. This would allow us to interrupt the circuit, turning the light bulb on and off because we were opening the circuit. Here's another example using a switch. In the same way, we can break the flow of current to turn the light bulb on and off. DC, or direct current, is defined by the flow of an electric charge in one direction. In DC current, the electrons move in one direction from an area of negative charge to an area of positive charge. This is unlike alternating current, where current can flow in both directions. DC current is the kind we'll be using to power our lights, and it uses 2 wires. Power, always the red wire, and ground, always the black. Power is the hot wire. This means if you touch it while grounded, you'll get a shock, albeit a small one since we're only using 5 volts. The ground wire allows the current to return to the power supply rather than the earth beneath us, completing the circuit. If the ground wire isn't attached, current won't flow through the circuit and your lights won't light. In general, always ensure that you connect the ground wire before you connect the power wire. 3 main factors in electrical circuits are voltage, the difference in electric energy between 2 points measured in volts, current, the rate of flow of electricity measured in amps, and resistance, how resistant your wire is to the flow of electricity measured in ohms. Larger wires have lower resistance than thinner wires, thus thinner wires lose more energy to heat than larger wires. Using a wire that's too small for the voltage and amps you're trying to pass through it is dangerous because it can start a fire. For 5-volt lighting, 16 AWG wire is usually sufficient for your power leads as long as they're not too long, and standard 18 or 20 AWG wire is fine for shorter jumper wires, like between 2 sections of strip. We can think of electricity like a water hose and voltage, current, and resistance in terms of this. For voltage, which is measured in volts, we might think of it as the pressure of the water going through the hose. For current, which is measured in amps and abbreviated as A or I, usually we think of this as the size of the hose. If it's a narrower hose, less water can get through at a time. If it's a wider hose, more water can get through. Resistance we calculate in ohms, which is usually written as R or the symbol for ohm. We might think of this as sand in the hose. This adds resistance to the water. So the more sand there is in the hose, the more resistance there is to the flow of water. The basic equation that governs the relationship between voltage, current, and resistance is the following. Voltage equals current times resistance. If you ever need to do so, you can solve for I to figure out which resistor you need to add in order to keep the current running through your LEDs below the suggested current on the datasheet. In practice, using a 300 to 500 ohm resistor as above will work for Neopixels. Neopixels usually draw about 20 milliamps when each is animated, and 60 milliamps if they're on white at full brightness. You can use this number to figure out how many amps you'll need for your power supplies. Many products, like our Neopixel matrix, also give a total amperage, or amperage per meter. In that case, use that to decide your power supply. Your voltage should match the voltage listed on the lights, within about 0.5 volts or so. You can get away with running Neopixels off 3 alkaline AAA batteries, for instance, because they provide 4.5 volts. Do not ever use a power supply that lists a higher voltage than your lights, plus 1 to 5% or so. For example, a 12-volt power supply with 5-volt lights. Applying a higher voltage to your strip will burn them out instantly. Be very careful to ensure that your power supply is always set to 5 volts if you are using a variable voltage power supply, like the bench power supply or 5-volt selectable supply. However, it's safe to slightly over-amp your projects. Since amps represent the potential rate of flow, it's not absolute magnitude. Choosing a power supply that provides about 20% more than the max amperage you plan to use will help decrease heat at the power supply and support the longevity of your lights. It's a good idea to do the math to ensure that your power supply provides enough amps to light your lights at full white, too. Otherwise, you could toast your power supply at midnight right before you present your project. Ask me how I know. Reading circuit diagrams is beyond the scope of this class, but it's good to know the basic diagram for an LED is as follows. This diagram shows the positive and negative poles on your power supply, the 2 flat lines, your resistor, the wavy V's, and the LED, shown as a diode, which is technically the D in LED, the triangle with the flat line. We talked earlier about brownouts, which might happen if you aren't giving your LEDs enough power. To solve this problem, we can use power injections. As a rule of thumb, it's usually safe to add a power injection after every 50 5-volt red, green, blue pixels. This means you can power about 100 RGB pixels with a power injection on both sides without cutting the strip. You can use this calculator to help you figure out where to add power injections. Enter the values for your LEDs from the datasheet for your product. Best practices include adding a capacitor across the plus and minus terminals of your power supply, where your power wires are connected. The capacitor will buffer any changes in the current drawn by the strip. You can also place a 300 to 500 ohm resistor at the end of your data line, right before the first pixel on your strip. This helps prevent surges that can burn out the first pixel. Jacketed 16-2 hookup wire, available cheap from DigiKey or Mouser, is perfect for running wires from your power supply to your lights. It's best to keep this run as short as possible, within reason. If you can put the power supply within a few feet of your lights, you'll cut down on heat generation and voltage drop. It's surprisingly easy to run 5-volt lights down to nothingness, just from the length of the power cable. You can also add JSTs or Molex connectors to the power pads on your strip and your power cables to make them easy to disconnect. To add power injections to a longer strip, you'll need to cut the strip. They usually have cut lines, and add jumper wires. Use 18 or 20 gauge hookup wire. Jump the data line straight across from data out to data in, and then connect power and ground to your external power supply. You can add JSTs or Molex connectors to make it easy to disconnect your power injections. It's fine to add more than one power injection to the same power supply. Just make sure you always leave about 20% headroom on the supply's total wattage. More on this later. It is important to ensure that the ground wires from all of your power supplies, as well as the ground pin on the Arduino itself, are connected. Otherwise, interference in ground loops can cause unpredictable color errors, which we call data noise, along your strip. Just ensure that your Arduino's ground pin and all the ground pins from the power supplies are tied together as you install. Heat control is also a factor in a successful LED installation. Where possible, attaching your LEDs to aluminum channel or another metal, usually double-sided thermal tape, will extend the lifetime of your LEDs and prevent failures due to heat buildup. We've covered a lot of information, and it's easy to be intimidated. But don't worry, start small if you're new to using LEDs, and then work your way up to the thousands and thousands of meters of pixels. It's important to know these concepts in order to work up to big installations, but when you're starting with less than 10 LEDs, you don't really have to worry about moving off the board or about external power. Feel free to start wherever you're comfortable and work up to the more complicated concepts. In Class 2, we'll go further with power injections and show how to use them. So don't worry if you didn't follow. Let's learn by doing and set up an LED strip or a matrix. The cable you bought for your DC power supply has 3 wires, hot, neutral, and ground. The wire colors correspond to these. Cords from North America and Japan often have black, white, and green or green and yellow striped wires. Cords from the rest of the world often have brown, blue, and green and yellow striped wires, which is fast becoming common in the US as well. See here for the color code for your cable. Once you're 100% sure which cable you have, remove it from the packaging, but don't plug it in yet. Strip the ends of all 3 wires to a length of about 1/2 inch. Then use a screwdriver to loosen the hot, neutral, and ground pads on the power supply. And insert each wire. Make sure not to leave any bare wire exposed. For safety, you want the stripped ends of the wires to be all the way inside each pad. Screw each pad down so the wire is securely fastened. Finally, triple check your wire order, as you can blow up your power supply by getting this backwards. Once you're happy with your work, I like to put a piece of electrical tape across the top of the pad so there's no chance that you could touch them or drop a tool and inadvertently short the connections. Some power supplies already come with a piece of protected plastic. AC line voltage is dangerous, so be careful. In the following section, we'd like to make sure that you have everything unplugged and unpowered. It's very important that you do not have power to either your microcontroller or your power supply when completing the upcoming steps. In order to attach our LEDs to our power supply, we're going to need to attach power and ground. So we'll need 1 wire for power, which is red, and 1 wire for ground, which is either white or black. Strip the ends of your wire to about 1/2 inch or so. Then we're going to want to undo the pads that are on the power supply. We want to undo 1 for power and 1 for ground. These are listed as V+ and V- on the power supply. Loosen the pads with a screwdriver so that you have enough space to insert your wire. Then secure your wire by tightening it with the screwdriver. Make sure no wire is exposed. This is our setup from earlier where we were powering the strips off of the microcontroller. We're going to need to make a couple changes in order to get this to work with our external power supply. Because we're going to be powering it off the power supply, we can remove power from the microcontroller. And then we'll connect it to power by clipping the other end of our alligator clip to the red wire. Now we have a clean connection of power from the power strip to power on our power supply, which again is +V or V+. We already have data connected to the data line on our LED strip. That's good, we don't need to change that. But we do need to change ground. All of the grounds need to be shared. So what we're going to do is that we'll take the end that's plugged into both of our grounds on our power strip, and we'll also connect it to our ground on our power supply. You can do this by twisting the wires and then clipping with the alligator clip. This is okay for a test setup, but if you're doing a permanent installation, you're going to want to use a connector. We'll talk about those later on. Make sure that your power and your ground lines aren't touching. It's very, very important that power and ground do not touch. You also want to make sure that data isn't touching power or ground. When everything's set, you can plug in your microcontroller and also turn on your power supply. And then you can upload your code to your microcontroller. You'll see a green light that indicates that the power supply is on. And then when you upload your code, you'll see your LEDs animate. So to recap, this circuit has a connection from ground all the way to ground of the strips, and then also to ground of the power supply. All grounds are together. We then have power, and that's going directly to the LED strip, to the power line. And then data is going from our microcontroller to the data line on our strip.
Hey, so I'm Cathy and I'm going to show you how to connect your LED matrix. Okay, so the first thing to do, make sure your power supply is set to 5 volts. As you can see, mine's set to 5 volts. And then make sure it's off, make sure the circuit playground isn't plugged in, everything's disconnected, and we're ready to start. So the first thing you need is a black alligator clip, and we're going to we need to connect all the grounds here, so we're going to connect it to ground on the circuit playground. There we go. And we're going to connect it to both of the grounds on the matrix. So this one in the middle and this one on the first part, the data in for the matrix. And I kind of like to just hold them together like this and put this guy on here, make sure it hits them both pretty good. And then you want to connect that to the ground on the power supply. And I usually just kind of chomp it on, in this case, just like that. Then slide these down to cover it. And make sure he's out of the way. You don't ever want this to touch the power, or your matrix will have a bad day. And then the next step is get a yellow or blue or green alligator clip. We're going to connect the data line, connect pin A1 on the circuit playground. And I've got my little resistor here, so just connect it like so. And if you have trouble with the resistor, it is perfectly fine to skip it. It's best practice, but these will work without it. So you've got that. You're going to connect that to the data in on this left side of the matrix. Then once you get that, the last step is to connect the power from the power supply to this 5-volt pin on the middle of the matrix, like so. And yeah, at that point, that's the 3 connections. You've got 3 grounds. The one from the circuit playground and 2 on the matrix are tied to ground on the power supply. You've got power on your matrix connected to power on the power supply, and you've got pin A1 run into data in on the matrix. Cool, so now we're ready to turn it on. I'm going to go upload code and come on back. Okay, and here we are. I've uploaded code and I'm ready to turn this on. The first thing we're going to do is power up the power supply. It's no big deal this time because we're not powering anything off the board, but if you are, you really want your power supply on first so that there'll be enough power for whatever lights you have plugged in. If you have too many lights plugged in, like running them off the board without like external power, it's very easy to make your Arduino freeze up because it can't power itself. So we're going to turn the power supply on first, turn it on or plug it in. And then we're very carefully going to plug in our microcontroller, just like this. Boop. And there you have it, it lights up. Yeah, make sure nothing shorts. You always want to keep ground and power like a good way away. Don't let those two touch. It's a bad idea. But anyway, yeah, this is a little bit washed out, but you can see our lovely patterns. And this file is on GitHub for you. It's called Color Palette Matrix. So yeah, check that out, and thanks for coming. See ya.
You now know everything you need to know in order to use a matrix or an external strip. Feel free to give it a try, and if you have any trouble, feel free to contact us during our office hour. See you next time.